Hi guys! A few years ago I published a tutorial on how to create a Spiderverse shader in Blender. It was one of my first tutorials and I received some feedback that it was too fast and hard to follow, so I always wanted to remake it. Now is a good time to do that, not only because there is a new Spider-Verse movie out, but also because Blender has changed a lot since then. The old tutorial was made with Blender 2.8 and we are now at 3.6, which means that we have vector math nodes instead of the simple maths node back then. We also have improved texture nodes, like an improved Voronoi node, and even multidimensional textures. This makes the whole process much easier than it was with Blender 2.8. Okay, so let's begin. I've prepared a basic scene that includes a Suzanne mesh, a ground plane, and some light sources. It is important to set the renderer to EV and not cycles. Unfortunately, the technique will not work well in cycles, and you will see why soon. First, we set the viewport shading to rendered to see all of our changes immediately. Now, in the shader editor, we create a new material for our object. In my example, I use the basic principled shader, but you can use any shader and complexity you want. Okay, so now let's get to the halftone dots pattern. The first thing we need to consider is how we want to map the pattern onto our object. In the movie, they used screen space coordinates, which means that the pattern is relative to the screen and not the object. For this, we create a texture coordinate node. This node offers two coordinates we could use, camera and window. To visualize the coordinates, we can use a checker texture node. As you can see, the camera coordinates also take the depth into account, which results in some distortion along the distance of the surface to the camera. It also causes the texture to be mapped in 3D space onto our mesh. If we switch the viewport to orthographic, the pattern shows no distortion, but we can still see the issue of it being mapped in 3D space. The window coordinates, on the other hand, works in both perspective and orthographic views. They are also mapped in 2D space and flat onto our object, but they depend on the aspect ratio of our viewport, which makes them appear stretched. We could compensate by simply scaling the coordinates based on the aspect ratio of our viewport, but we could also adjust the camera coordinates, which is in my opinion the more elegant way. Let's create a separate XYZ node to isolate the z-axis of the coordinates. Then we divide the camera coordinates with a vector math node by this value. You can see that it works in our perspective view, but it shows distortion in orthographic view. For now, we create a switch so we can toggle which coordinates we want to use based on the perspective we are using. Unfortunately, with shader nodes, we cannot create a toggle with a Boolean statement, but we can use a workaround. Create a mix node and set it to vector. Plug the raw camera coordinates in the top and our adjusted coordinates in the bottom input. The factor slider now acts as a simple toggle where 1 means that the view is perspective and 0 that it is orthographic. So if you are using a perspective viewport or camera, turn the value up to 1, and if you are using an orthographic camera, set it to 0. We still have the issue that the pattern is mapped in 3D space, as we can see in orthographic view. To fix this, we simply take a vector math node and set it to multiply. We only multiply the x and y coordinates by 1 while cancelling out the z component by multiplying it with 0. This converts our coordinates from 3D to 2D. Now everything works as expected and we can switch the coordinates based on the perspective we are using. To organize, create a frame around our coordinate nodes by pressing Shift P and call it Screen Coordinates. We can also color our mix node to make it more distinct. I choose a bright pink color. Now that we have our coordinates set up, we need to create the dots pattern. I will show you two ways, the easy and fast way and a slightly more advanced method which will be a little bit more performant. For the easy and fast method, we create a Voronoi texture node and set it to 2D since we don't need the third dimension. Let's have a look at the distance output. If we decrease the randomness slider to 0, we will get this nice uniform pattern of spherical gradients. Scale up the pattern by adjusting the scale value. I use a scale of 40 for now. If we now use a math node set to less than, we can compare the value range of the gradient with the threshold input field. We want our gradients to represent the whole range from 0 to 1. I'll spare you the mathematical details, but we can achieve this by simply multiplying the gradient with the square root of 2. Just type sqrt open bracket 2 closed brackets into the input field of the math node. Now the value goes from 0, which is black, to 1, which represents white. Let's convert our shader to a data type that our math node can process. For this, we use the shader to RGB node, which converts the shader to color data. Remember, I've said our technique will not work in cycles. That's because the shader to RGB node unfortunately only works in Eevee. Anyways, if we now plug this data into the threshold of our less than node, we can see that the pattern reacts to this value. Now we only need to adjust the contrast of the RGB input. A simple and visual way of doing this is by using a color ramp node. There is still a small problem with this method. The pattern is inverted. You might like it this way, but to make a proper halftone dots pattern, we need to invert our base pattern. We could do this with a color ramp by simply switching black and white, but there is an easier way to do it. Create a math node set to subtract and subtract the pattern from 1. This will result in an inverted pattern. If we now look at the result of our shader, we can see that the halftone pattern is now correct. Select the subtract node and press M to mute it and see the difference. Now select all of these pattern nodes, create a frame by pressing Shift P and call it dots pattern. But like I said, there is a more advanced and more performant method to create this pattern, as the Voronoi node does some calculations we don't need. Let's disconnect our first pattern for now. Now create a vector math node and set it to scale. This simply scales our coordinates. Duplicate the vector math node and set it to fraction. This results in this repeating pattern. Duplicate the vector math node one more time and set it to distance. By setting the x and y inputs to 0.5, we will get a pattern that is similar to our Voronoi pattern. It just has a slight offset, which is not relevant for our use case. Now we can grab and duplicate the multiply and subtract nodes from our first setup and plug them into the less than node. As you can see, the halftone pattern looks the same, but without using the Voronoi texture, it is a little bit faster to render. Again, create a frame around all the pattern nodes and also name it to dots pattern. Then I color the subtract node to highlight that it acts like a toggle to invert the pattern. Now we can delete the old pattern that is based on Voronoi, as we don't need it anymore. We now have our dots pattern, but what about the line pattern, you might ask? Well, this is even simpler. We could use a wave texture node. Then we set it to saw, and we use that as an input for our less than node. But again, we can optimize this step. Create a separate XYZ node and isolate the X coordinate. Then create a math node and set it to multiply. Duplicate it and set it to fraction. With the multiply node, you can adjust the scaling of the pattern. This looks similar to our first pattern, right? Now simply connect it to the less than node to see the result. To control the direction of the pattern, create a vector rotate node and plug it right before our separate XYZ node. You can leave it at the default settings, as we want to rotate it about the Z-axis. Create a frame around the pattern nodes and call it line pattern. We could stop here if we only want the true halftone look. But we can also use this pattern to manipulate data fields in other shaders. For example, we can plug it into an mix RGB node to control the colors individually, like I do here. What if we want a more advanced Spiderverse-like shader? Well, with our base patterns we can easily recreate any effects we want. Let's move our pattern nodes out of the way for a moment. First, I create a principled BSDF node with a simple image texture plugged into its base color input. Let's say we want our shadows to have a line pattern, while the highlights should have a dots pattern. First, adjust the line pattern to your preference. You can adjust the threshold for the shadow area with the color ramp node, the scaling with the multiply node, and the direction with the vector rotate node. Let's mix this with our base texture by using a mix color node set to multiply. Adjust the strength of the effect with the factor slider. Reorganize the nodes and create a frame for the final output of the line pattern. For the dots pattern, duplicate the color ramp and less than nodes from our line pattern and connect the shader to RGB node and the dots pattern to them. Here we want the inverted pattern, so I disable the subtract node by selecting it and pressing M. Adjust the color ramp to let the pattern only appear on the highlights. Now you can rename the frame to dots. Let's duplicate the mix color node and set it to add. Now we can connect it to the dots pattern. We can lower the strength by adjusting the factor slider. The material now looks really close to what I wanted. But there is one last step I want to do. I want to use the dots pattern for the roughness input of the principled shader. If we use the pattern directly, all the black areas will have a roughness of 0 and all the white areas will have a value of 1. To control the roughness, we can use a map range node. A map range node is very similar to a color ramp. The toMin input remaps the black areas to a value we want. In this case, I choose 0.3. This is equivalent to setting the left side of the color ramp node to a gray value. With the toMax input, I adjust the roughness in the white areas of the dots pattern. I set it to 0.5. Now I'm very happy with the shader. Remember, you have to switch your coordinates based on the perspective you are using. To organize the node tree better and to make the patterns reusable, you might want to create node groups out of them. But this is not part of this tutorial. If you are interested in a more advanced setup, With a lot more features and other cool halftones and NPR effects, you might want to check out the Trips NPR package I've put up on my Gumroad page. It offers 9 easy-to-use and highly adjustable shader node groups, over 40 material presets, and a completely procedural outline node group, all packaged as an asset library for easy reusability across all of your projects. Use the link down below for a 30% discount. I appreciate that you have watched this tutorial and I hope you've liked it. Leave a thumbs up if it helped you and maybe consider subscribing to my channel. See you next time.